Well, in this annoyingly dense chapter, we have to be, a little more forthcoming with a lot of things. In this particular question, we have a lot of work to do with the approximation schemes once again, so let's dive in. A point charge Q of mass m is attached to a spring of constant K. At time t equals 0, it is given an initial kick, so its initial energy is U0 equal 1/2 mv0 squared. Now it oscillates, gradually radiating away its energy. A. Confirm that the total energy radiated is equal to U0. Assume that the radiation damping is so small that you can write the equation of motion as x double dot is equal to, or x double dot plus gamma x dot plus omega naught x is equal to 0. And we have this solution. Again, that's a homogeneous equation. We get a couple of coefficients. So we're going to have a transient term and then the repeat term, sine theta, which is more steady state. But anyways, we see that omega naught is equal to square root of k over m. Gamma, therefore, is equal to omega naught squared times tau, where gamma is much less than omega naught. Okay. B, suppose now that we have two such oscillators and we start them off with identical kicks. Regardless of their relative positions and orientations, the total energy radiated must be 2 U0. But what if they are right on top of each other? So it's equivalent to a single oscillator with twice the charge. The Lamar formula says that the power radiated is 4 times as great, suggesting that the total power will be 4 times U0. Find the error in this reasoning and show that the total energy is actually 2 U0, as it should be. Okay, well, we have the Abraham, Lorentz, and the Lamar formulas as such again. So let's dive in. So from the Abraham-Lorentz formulas, we can rewrite the radiation reaction force to something a little more tidy, i.e. F rad is equal to mu0 q squared over 6 pi c a dot. Well, here, if we add in the m, so we divide it by m, so we multiply it by m, and then we use the substitution tau, which we had, several chapters ago, I believe in chapter 9, where it was used, maybe chapter 10, I don't remember. But anyways, tau was a common factor for the mu0 q squared over 6 m pi c. So that's why we just added another m, since we don't have one present. But nonetheless, what we see is that a dot is actually x triple dot, since we need the third derivative with respect to time. So the equation of motion based on the sum of forces is equal to F spring plus F radiation is equal to ma. Well, if that's the case, we just have negative kx plus m tau x triple dot is equal to m double dot. Okay. Here, if we set this equal to 0 and put everything to the same side, we have a homogeneous equation. Here, we know that if we divide by m, we get x double dot plus k over m, which just goes to omega naught squared. That's common. Minus tau x triple dot. But here we're saying that since the damping is so small, it oscillates at natural frequency omega naught, or that it's negligible. And hence x triple dot is equal to actually the negative omega squared of x dot. Again, since it's oscillating with respect and repeats itself, that's a fair assessment to make. So now our equation gets modified to just a second order equation, since it repeats itself, and all the terms have a omega naught, or now have an omega naught. So we can let gamma equal tau omega naught squared, and we see the reduction in this equation. Again, still homogeneous, second order, so we know what the solutions to expect are. And so x naught at 0 for gamma much less than omega naught. And so with that being said, we have our condition there. Take the derivative with respect to time, and we see we get a product rule. So we see that V naught, once we apply all the conditions, we can solve for what A is. Again, x naught, x at 0 equals 0 gets rid of the other part of the transient solution that had to deal with cosine. Here we're just taking a derivative to find A, which is A is the ratio of V naught over omega naught. Hence how we find the equation of motion of x of t as such with the given substitutions. We see how we were given those in the equation, in the statement. Now we see where they come from and trying to solve this thing and simplify it. So let's continue. So then according to the Lamar formula, the power radiated is P is equal to mu naught Q squared A squared over 6 pi C. In this case, still assuming that gamma is much less than omega naught, A is equal to negative omega squared x hat, or x. So if we plug in x with everything, we see that we get the omega naught canceling from the A factor, the constant factor. And we see that we get negative omega naught v naught e to the negative gamma t over 2 sine omega t. If we plug that in and we square it, as is required for the Lamar formula, we get something pretty gross, in my opinion, which is mu naught qt, or q squared over 6 pi c, omega squared v, omega naught v naught squared. That 2 that goes from the exponential gets canceled with the square. We like that. But we also have a sine omega naught t squared term now. But here, if we're averaging over a full cycle, holding the exponential term constant, we get that 1/2 again. Again, exponential terms they're not going to, with gamma being so small here, the exponential term is going to look constant with respect to the full cycle. So, get rid of that sign that we have with the 1/2, and the total energy radiated now goes from 0 to infinity in the integral form of the average power P. So let's go ahead and integrate away. We get the gamma term there, which goes to 1 over gamma, or the exponential term there, which cancels down in the integral form to 1 over gamma after evaluation. Okay, so plug in the gamma, which is omega naught squared tau, and the omega naught squared terms cancel. Tau gives us a 6 pi mc over the mu naught q squared because it's 1 over tau. As you see, mu naught q squared cancels. We have a cancellation of 6 pi and c with the denominator. That reduces to 6 over 2, or 6 over 12, excuse me. So just the pi c terms cancel. And we're left with 1/2 mv squared. I don't know. That's pretty cool to me. How we can start with something and end exactly where we need to. The big thing here is that the assumption of gamma being much less than omega naught makes us hold that exponential term steady. Okay. So here then what we need to consider for part B is this equivalent single oscillator has twice the charge and twice the mass. So tau and hence gamma to the 4th, or gamma, is doubled. Since what we just saw in the last step, or the last part of the question, was that the integral over time of the average power is some kind of factor of q squared over gamma, it also doubles. If we double q, right, 2q squared gives us 4q squared. Okay? That's just a scaling law. But then since gamma goes to 2 gamma, the 4 and the 2 factors cancel to 2, and so it also doubles. The power radiated is indeed 4 times as great, but the oscillations die away faster, and the total energy power radiated is just twice as much for one oscillator. So it actually works out altogether pretty well.